Welcome to this tutorial, where I'll walk you through setting up a real-time sentiment analysis system using the Yelp dataset from Kaggle. As you can see from the architecture diagram here, our system involves multiple components working together seamlessly to process and analyze large streams of data in real time. This architecture starts with the Kafka producer, which captures live data from the Yelp dataset hosted on Kaggle. The data is ingested into the Confluent Kafka platform, where it's processed and structured. From there, we utilize Apache Spark for data streaming and processing, which feeds the data into MongoDB Atlas for temporary storage. For sentiment analysis, we're leveraging HuggingFace's DistilBERT base uncased fine-tuned SST2 model to classify Yelp reviews in real time. The processed data is then stored and indexed in Elasticsearch and finally visualized in Kibana, which gives us real-time insights into the sentiment of the reviews. Throughout this video, I'll take you step by step through the setup and integration of each component, starting with creating a Kafka cluster on Confluent Cloud, setting up Spark for stream processing, integrating the HuggingFace sentiment model, and finally setting up Elasticsearch and Kibana for real-time visualizations. By the end, you'll have a fully functioning pipeline that ingests, processes, analyzes, and visualizes data in real time. Let's dive into how each part of this system fits together. In the first step, search Kaggle on Google and head over to kaggle.com. If you don't already have an account, click Register. You can sign up quickly using your Google account. Select your Google account, continue, and complete the registration process. If the username is already taken, try a different one and proceed. Once registered, agree to the privacy and terms to finalize. Next, head to the Dataset section. In the search bar, type Yelp. Inside the Yelp dataset, scroll down and select the business.json file. You'll see that this file contains various details such as business ID, name, address, city, state, longitude, latitude, and more, which are key to our analysis. Now let's move on to setting up Elasticsearch and running the bulk upload process to insert business data into our index. First, search for Elasticsearch on Google and head to cloud.elastic.co. Start a free trial, then sign up using your Google account. Select your account and proceed by filling out the required information. This includes details about your company, your experience level, and your interest in Elastic. Once that's done, it's time to create the deployment. For this deployment, we'll be using AWS and selecting the Frankfurt region, as we'll be using this for all our platforms to keep data flow smooth. Name the deployment Yelp Deployment, then click Create Deployment. This process will take some time to get ready. Once it's done, you'll be provided with an Elasticsearch user and password. Make sure to download or note these details for later. Next, we return to Kaggle. Go to the settings, change the theme to dark, and complete phone verification. This will enable internet access in our Kaggle Notebook sessions, allowing us to use T4 GPUs for additional computational power, which is especially useful for machine learning tasks. Now, let's create a new notebook. Name it Elastic Bulk Upload. Start by removing the sample code and ensure internet access is enabled. Add the Yelp dataset to your notebook environment. First, install Elasticsearch by running the command !pip install Elasticsearch. Once installed, we'll move to writing the bulk upload code. In this snippet, we're working with Elasticsearch and the Yelp dataset. First, we import the necessary libraries, Elasticsearch and helpers from the Elasticsearch module to interact with Elasticsearch, and JSON for handling JSON data. Next, we establish a connection to our Elasticsearch cloud instance. We use the Elasticsearch class, providing the URL for our Elasticsearch deployment. In this case, it's a placeholder where you'll insert your specific endpoint. Additionally, we disable certificate verification by setting verified_certs equals false. For basic authentication, we include the username and password, which you'll also need to replace with your own credentials. Now, we proceed to open the Yelp dataset file. We use the open function to read the file located in the Kaggle environment. The file contains business data in JSON format, so we initialize an empty list called data to hold the processed documents. We loop through each line in the file, attempting to load each one as a JSON object. If successful, the object is appended to the data list. In case of any JSON decoding errors, we handle them gracefully using a try-except block and print the error to the console. Once all the documents are read, we use the helpers.bulk function from Elasticsearch to upload the data in bulk. This function takes our client as the connection, the data list containing our documents, and the name of the index where the data will be stored, which you'll need to specify. And with that, the business data from Yelp is uploaded to your Elasticsearch index. Once the code is ready, return to the Elasticsearch portal and change the theme to dark by using the drop-down in the top right corner of the page. Then, go to the left drop-down and open Manage this deployment in a new tab. In the Applications section, copy the Elasticsearch endpoint URL and paste it into the endpoint URL section of your notebook. Next, go back to the Manage this deployment tab and under the Security section, reset the password for the Elastic user. Copy the password, then fill in the basic authentication fields in your notebook. Use Elastic for the username and paste the copied password into the password field. Once that's done, return to the Elasticsearch portal and navigate to the Management section from the left panel. Under Index Management, create a new index and name it Businesses. The index is now created but empty. Back in Kaggle, run the notebook cell to upload the business data to the business's index. There will be warnings about insecure request warning due to unverified HTTPS requests. This is expected and not a problem for us. Returning to the Elasticsearch portal, under Index Management, You can see the documents being loaded rapidly, starting from 34,000 documents and eventually reaching around 150,000 documents, approximately 185 megabytes in size. With that, the data is successfully uploaded to the index. Returning to Kaggle, we now focus on the reviews.json file from the Yelp dataset. This file is significantly larger than the business.json file, weighing in at 5.34 gigabytes. Given the size, it contains a wealth of data. The columns in this file are essential to understanding how users engage with businesses and their reviews. There are 9 key fields. Review ID, a unique identifier for each review. User Onch ID identifies the user who wrote the review, allowing us to track individual reviewers. Business Docs ID. This is a crucial field, as it serves as the common key to join the data from the businesses.json file, which we've already uploaded. Stars represents the star rating the user gave the business, from 1 to 5. Useful, funny, cool. These fields track how many people found the review helpful, humorous, or cool, respectively. They provide insights into how other users engage with the review. Text. This is the actual content of the review, where sentiment analysis will come into play. Date. The date the review was posted, useful for tracking trends over time. We'll later utilize this business ID field to join this dataset with the businesses.json file we uploaded to Elasticsearch, allowing us to link reviews to specific businesses. The large text fields will be valuable when performing sentiment analysis using the HuggingFace DistilBERT model. Next, we head over to Confluent to set up our real-time data streaming pipeline. First, search for Confluent on Google and navigate to confluent.io. If you haven't done so already, sign up for an account or log in. You can sign in with Google for quick access. Once inside Confluent Cloud, go to Environments and add a new cloud environment. Name it Yelp_environment. Now, it's time to create a Kafka cluster. Select the basic plan for simplicity, then configure it by selecting AWS as the cloud provider and Frankfurt as the region. Similar to our previous Elasticsearch setup for data flow consistency. Name the cluster Yelp cluster and launch it. After the cluster is set up, go to the API keys section from the left pane. Here, create an API key for your account, download it, and save it securely as it will be required for later steps when connecting Kafka. Now, go to the cluster settings section. This is where you'll find the Bootstrap server address. This will be important later when we connect our Kafka producer to the cluster. Next, we need to set up a Kafka topic. Head to the topic section and create a topic named raw topic. Finally, we need to define the schema for our messages, as we want to enforce a consistent structure for the data. Select Avro schema and remove the sample schema provided by default. Then, paste in the correct Avro schema that we prepared for our raw reviews data. This schema ensures that all messages follow the same structure, particularly useful for ensuring compatibility when multiple consumers are reading from the same topic. After creating the topic and schema, the raw topic is now set up and ready to receive data. However, it's still empty at this point. In the next steps, we'll write a Kafka producer to stream the Yelp reviews.json data into this topic for real-time processing. Start by opening a new Kaggle notebook and name it Kafka Producer. In the first cell, write the following command to install the necessary library: pip install Confluent Kafka. Afterward, add the Yelp dataset as an input to the notebook. Additionally, we need to adjust file persistence settings from the notebook session options. This ensures that if the notebook restarts or is interrupted, the Kafka producer can continue where it left off, maintaining the stream's integrity and processing flow. Run the first cell to install the package. Now let's focus on writing the core of the Kafka producer code. We'll be writing a Python script to read the Yelp reviews from the JSON file and produce these messages to our Kafka topic. First, we'll start by importing the necessary libraries. We need JSON to handle our JSON data, OS for file operations, pandas for handling timestamps, and the producer class from Confluent Kafka to connect to our Kafka instance. Next, we'll set up our Kafka producer configuration. This is where we define how our producer connects to the Kafka cluster. We create a dictionary called conf to store our configuration settings. Within this dictionary, we'll specify the Bootstrap server. This is crucial as it tells the producer where to find our Kafka cluster. You should replace the placeholder with your actual Kafka Bootstrap server address. Next, we configure the security protocol to use SASL SSL for secure communication. We'll also specify the SASL mechanisms and provide our Kafka API key and secret, which are essential for authentication. These will be inserted into the sasl.username and sasl.password fields, respectively. Lastly, we set a client ID to identify our producer application. After setting up the configuration, we create an instance of the producer class using our conf dictionary. This initializes our Kafka producer, ready to send messages. Now, we need to define the topic name where we will be sending our messages. In this case, we assign the variable topic to the string raw topic. Next, we will create a delivery report callback function named delivery report. This function will be called after a message is sent to Kafka. Inside this function, we check if there was an error during the message delivery. If an error occurred, we print an error message indicating that the message delivery failed, along with the error details. If the message was delivered successfully, we print a confirmation message that includes the key of the delivered message. Following this, we'll implement a function to read a checkpoint from a specified file. This is important for resuming the message production after an interruption. The function, readCheckpoint, takes a checkpoint file as an argument. It checks if the file exists. If it does, it opens the file, reads the last successfully sent message index, and returns it. If the file doesn't exist, we return 0, indicating that we haven't sent any messages yet. Next, we will define a function called writeCheckpoint. This function takes the checkpoint file and the current index as parameters. It writes the current index to the checkpoint file, allowing us to keep track of which messages have already been sent. After updating the checkpoint, we print a message confirming the updated index. We also need to handle dates within our JSON records, so we'll define a function called handleDate. This function checks if the object passed to it is a pandas timestamp. If it is, it formats the timestamp into a string format. If it encounters an object of a different type, it raises a type error, indicating that the object is not JSON serializable. Now, we're ready to write the main function that will handle the streaming of our JSON data. We'll call this function stream JSON serially. It takes the path of the JSON file and an optional checkpoint chart file argument, defaulting to a specific location in the Kaggle working directory. Within this function, we first read the last sent index from the checkpoint file. This tells us where to resume processing the JSON lines. We then open the specified file path for reading. As we read through each line of the file using a for loop, we check if the current index is less than the last sent index. If it is, we simply skip that line. For each line, we attempt to decode it from JSON. If successful, we call the producer produce method. Passing the topic name, the review ID as the key, and the record as the value. We use the JSON dumps function to convert the record to a JSON string, applying our handleDate function to ensure any dates are formatted correctly. After producing the message, we call producer.flush to ensure that the message is sent to Kafka immediately. Then, we update our checkpoint file with the new index to indicate that this line has been processed. If a JSON decode error occurs at any point while reading the file, we catch that exception and print a message indicating the failure to decode that specific line. Finally, we include a conditional statement to check if the script is being run as the main program. If so, we call our stream JSON serially function. Passing in the path to the Yelp reviews JSON file. This completes the Kafka producer setup, allowing us to efficiently stream our Yelp reviews to Kafka, where we can further process them as needed. Next, go to the Confluent Cloud dashboard, navigate to the cluster settings, and copy the Bootstrap server address from the endpoints section. Paste this into the bootstrap.servers configuration. Next, go to API keys, create a new API key, and copy both the API key and secret. These will be your Kafka credentials. Paste the API key into the sassel.username field and the secret into the sassel.password field. For the Kafka topic, go to the Topics section on Confluent, find your topic, in this case, raw topic, and add that name to the topic configuration in the notebook. After writing the code, run the Kafka producer notebook to start sending messages. If the notebook is interrupted, we want it to be able to recover and continue processing without data loss. To check this, insert a simple cell containing !pip show confluent_Kafka to ensure that the package remains installed even after restarting or interrupting the notebook session. This persistence is key in maintaining a long-running producer without losing progress. Run the main producer cell. If any errors like a syntax error appear, such as using a single equal sign instead of double equals in condition checks, fix them and rerun the cell. Now the Kafka producer will begin streaming messages from the reviews.json file into the Kafka topic raw topic. To verify that the data is flowing properly, go back to Confluent, navigate to the topic section, and open raw topic. Inside the Messages tab, you should see the incoming messages from your notebook, all adhering to the defined schema. This confirms that the Kafka producer is functioning correctly and streaming data in real time. Next, cancel the current run. Restart and clear outputs from the notebook and stop the session. Finally, as a demonstration of how the notebook recovers from interruptions, run the producer again. After restarting the session, check if the notebook continues from the last processed message, confirming the checkpoint is working. The messages will resume from where they left off, message 163, and the checkpoint will update accordingly, ensuring no data loss during interruptions. First, open a new tab and search for MongoDB Atlas. Go to the MongoDB Atlas website and click on Start Free. Sign up with Google, choose an account, and continue. After accepting the privacy policy, MongoDB will ask you some questions to get to know your project better. Things like your primary goal, how long you've been developing, and the types of data you're working with. Once you've filled these out, the system will automatically redirect you to deploy your first cluster. For this, choose the M0 cluster tier, which is free and suitable for exploring the cloud environment. You'll also want to make sure to select AWS as the cloud provider and Frankfurt as the region to keep it consistent with our other deployments. When naming the cluster, use Yelp cluster. Note that MongoDB doesn't allow underscores in the cluster name, so Yelp cluster with a dash will work just fine. Once you've done this, click Create Deployment. While your cluster is being initialized, navigate to the Network Access section on the left-hand menu. Click on Add IP Address and select Allow Access from Anywhere. Click Confirm to save these changes. Next, we need to create the database users. Go to the Database Access section and click Add New Database User. For the first user, set the username to Spark. For the database user privileges, choose the built-in role Atlas Admin. This user will be used for Spark streaming in the upcoming steps. Once you've done that, click Add User. Now create a second database user with the username Mongo source and password Mongo123123. For this user, set the privileges to read and write to any database. This user will be used later with the Confluent Mongo source connector, which will handle the data flow between MongoDB and Kafka. At this point, your MongoDB cluster, Yelp cluster, should still be initializing, so let's shift over to Confluent. Now, in the Confluent Cloud, go to Topics from the left-hand menu and create a new topic. The topic name must match the MongoDB database and collection we're going to create later, so name it ReviewsDB.Enriched Reviews Collection. Once the topic is created with default settings, click on Create Schema. You will now add the schema structure for this topic. It's essentially the same as the schema for the raw reviews data, but with an additional field for sentiment. After pasting the schema structure into the editor, click Create. The new schema is now set up, but the topic is empty and waiting to receive messages. Back in MongoDB Atlas, your cluster should be ready by now. Go to the overview page of your cluster and click Connect to see the connection string URI. This is important as it contains the details for connecting external applications to MongoDB. Copy this connection URI for later use when setting up the MongoDB source connector. Now let's create the actual database and collection that we will use to store the enriched review data. Go to Collections, and MongoDB will have a sample database and collections pre-initialized. We'll create our own by clicking on Create Database. Name your database ReviewsDB and the collection Enriched Reviews Collection. It's crucial to ensure that this collection name matches the Kafka topic we created earlier. Once named, click Create. At this point, the collection is ready and waiting to receive documents, just like the Kafka topic is waiting to receive messages. Finally, let's head back to Kaggle, where we will create a new notebook to handle Spark streaming. This wraps up the MongoDB Atlas and Kafka topic configuration portion of the setup. Now, we're ready to move on to Spark streaming and data processing in the next step. Let's now walk through the process of setting up the PySpark streaming notebook, integrating Kafka, MongoDB, and HuggingFace for sentiment analysis in detail. Set the session options to use a GPU T4 accelerator and enable file persistence so that if the session is interrupted or closed, it can continue from where it left off. name the notebook Spark _stream _Kafka _Mongo. Next, remove the sample code provided in the notebook and move on to installing PySpark. In the first cell, type pip install PySpark == 3.5.2 and run the cell to install PySpark. We'll start by setting up Spark, importing necessary libraries, and defining our Kafka and MongoDB configuration. First, we import the required PySpark modules: Spark session to create a Spark session, from JSON and call for manipulating the streaming data, and UDF for creating user-defined functions. We also bring in struct type, struct field, string type, integer type, and float type for defining the schema of our Kafka messages. Then, from the transformers library, we import the pipeline function. We also import the logging and OS modules to manage logs and file paths. Next, we configure logging to only display errors and we create a checkpoint directory where Spark will store its progress. This directory ensures that if our notebook restarts, the stream continues processing from where it left off. If the directory doesn't exist, we create it using os.makeDirs. Now, we define the config dictionary, which holds our Kafka and MongoDB credentials. This includes the Kafka Bootstrap server, API key, and API secret. For the Kafka credentials, copy the same ones we used in the Kafka Producer notebook. For MongoDB, we specify the URI, database name, and collection name where the enriched reviews will be stored. For MongoDB, go to the MongoDB Atlas cluster, click on Connect, select drivers, and copy the connection string from there. You will need to replace the username and password with the credentials we created earlier for the Spark user. Username, Spark. Password, Spark1231123. Now, to integrate sentiment analysis, go to HuggingFace by opening a new tab. On their website, navigate to the Models section and filter by text classification models. Sort by most downloads, and you should find a model called DistilBERT Base uncased fine-tuned SST2 English. Click on the model, and on the model page, you'll find an option to use this model. Copy the string provided, as we'll need it later for the sentiment analysis pipeline. Now, return to the notebook. We define a function analyzeSentiment that takes text as input and returns the sentiment label, like positive or negative. We also wrap this function in a user-defined function, UDF, called sentiment UDF, which allows Spark to apply it to the streaming data. Now, we move to the core function, read from Kafka and write to Mongo. This function reads the streaming data from Kafka and writes the enriched data with the sentiment analysis to MongoDB. And to read the streaming data, specify the topic name. The raw reviews topic is named raw topic, which is where our Kafka producer is currently sending messages. First, we define the schema of the Kafka messages using struct type. The schema includes fields like review ID, user ID, business ID, stars, useful, funny, cool, text, and date, all of which come from the Yelp reviews dataset. Then, we configure the Kafka stream by specifying the Kafka Bootstrap server we subscribe to the raw topic, which is the Kafka topic containing raw reviews. Security protocol. and SASL authentication settings. The Kafka stream data arrives in a binary format, so we need to parse it. We convert the raw Kafka messages into a structured data frame using from JSON, applying the schema we defined earlier. This gives us a structured data frame with all the fields we need. Next, we enrich the parsed data frame by adding a new column called sentiment. We apply our sentiment UDF to the text field, which contains the review text, and the UDF classifies each review as either positive or negative. Finally, we write the enriched data frame to MongoDB. We use Spark's writeStream function, specifying MongoDB's connection details. The checkpoint location points to the directory we created earlier, which ensures that the stream's progress is saved. We specify the required jars using spark.jars.packages. These are the Kafka and MongoDB connectors needed to work with both systems. Go to the Maven repository website and search for Spark SQL Kafka. Select the version that matches our PySpark setup, which in this case is 3.5.2. Click on Gradle, Kotlin, and copy the library string provided. Next, go back to the Maven repository and search for Mongo Spark connector. Again, select the latest compatible version and copy the library string from there. Now that we have all the required dependencies, once the code is written, let's check if the notebook is still alive and running. However, we forgot to select the GPU accelerator, so we'll go ahead and add that now. As the notebook restarts, we'll need to reinstall PySpark, so rerun the first cell pip install PySpark. Go to MongoDB Atlas and open the enriched reviews collection to monitor when our streaming process starts. Also check Confluent under raw topic to ensure the messages are still being sent from the producer. Next, run the main code cell, which contains the streaming script. Here, we encounter an indentation error in the if block. The indentation is too deep, so we'll reduce it to the lowest level of indentation. After fixing that, we run the code again. Now, another error appears. which is a typo. In the Spark Session Builder. We forgot to include the equal sign between Spark and Spark Session Builder. Let's add the equal sign and rerun the cell. The next error we run into is a PI4J Java error, which is caused by a version conflict between the JR files. We mistakenly specified the wrong Scala version when pulling the JR files from Maven. Our environment uses Scala 2.12, but the JR files we chose were for Scala 2.13. Let's go back to Maven, search for the 2.12 versions of the required libraries, and update our code with the correct versions. At this point, the notebook should be restarted again to ensure the environment is reset with the correct libraries. After restarting, reinstall PySpark, pip install PySpark == 3.5.2, and rerun the main cell. This time, the code runs smoothly, and the streaming process begins. Once you run this notebook, it will continuously read reviews from Kafka, classify their sentiment using HuggingFace, and write the enriched reviews to MongoDB. This process will keep running until the notebook is manually stopped. Now go to MongoDB Atlas and check the enriched reviews collection. You should see the first few documents arriving in the collection. After a short while, check again, and you should see around 160 documents with a new sentiment field, indicating that the HuggingFace model is successfully classifying the sentiment of each review. More than 200 messages have now been streamed into the MongoDB collection, and there are still many more messages to process in the raw topic. Around 13,000 messages total. The streaming process is catching up slowly, but it's working as expected. Finally, we'll go back to the Confluent platform, navigate to the connectors page, and create a source connector for MongoDB Atlas, ensuring our data flow is properly connected. We start by going to the Confluent connectors page and selecting the MongoDB Atlas source connector. For the topic prefix, we leave this field blank. Click Continue, and on the next page, generate an API key for the connector and download it. Click Continue again, and we'll now provide the MongoDB Atlas database details for the connector. To do that, we'll need the following information. Connection host. To get the connection host, we go to MongoDB Atlas. Open our cluster overview, click on Connect, select Drivers, and copy the host URI. Connection user. The MongoDB read-only user we created earlier, Mongo source. Connection password. The password we set, Mongo123123. Database name, ReviewsDB. Collection name, Enriched Reviews Collection. For the Kafka record value format, we select JSON to ensure the data is serialized correctly. We also enable the Publish Full Document Only option, so that each document from MongoDB is sent as a complete record to Kafka. Single message transforms. We now scroll down to the Transform section to add single message transforms. For Transform 0, we select the Value to Key transformation. This allows us to move the Review ID field to the key of the Kafka message. We specify the field as Review ID since this is the unique identifier we want for our Kafka records. We select the extract field $key transformation type. This ensures that the key field contains only the review ID, making it the key for each record in Kafka. Remove the _ID field, which we don't need in our Kafka topic. So, for Transform 2, we select the Replace Field Value Transformation type and add the _ID field to the blacklist. This ensures that the _ID field is removed before the document is written to Kafka. We then click Continue to move to the next steps and finalize the connector configuration. The connector will now provision itself, and after a short delay, it should be up and running. With the connector now running, we go back to MongoDB and check our enriched reviews collection. We can see that 2,600 documents have already been streamed into the collection by our Spark stream. These documents will now be transferred to Kafka via the MongoDB source connector. Let's go back to Confluent and look up our topic ReviewsDB.enriched reviews collection. We can see that 151 messages have already arrived via the connector, and everything looks clean and healthy. We refresh the page, and now 300 messages have arrived, indicating that the data is flowing correctly and at a steady pace. Now that the MongoDB Atlas source connector is working successfully, the data is streaming from MongoDB into Kafka. The setup is complete, and the data is being processed and enriched without any issues. Next, we can move on to configuring Elasticsearch for indexing and performing additional analysis on the streaming data. Step 1. Creating the reviews index with schema. First, we navigate to the Management section of Elasticsearch and click on Index Management. From there, We open the console at the bottom of the page. We remove any sample commands in the console and paste in the index creation command we prepared earlier, which defines the appropriate data structure for holding the enriched reviews after the Kafka sync connector processes the data. After running the command, we receive an index created successfully message, indicating that the reviews index has been successfully set up. We need to create an enrichment policy to extract relevant fields from the business's index. While this can be done via the UI, we'll use the console for this process. We paste the command to create the enrichment policy, which specifies which fields we want to extract and transform. After running the command, we get an acknowledgement with a message. Acknowledged, true, confirming that the policy has been successfully created. Now, we close the console and go to the Enrich Policies section under Index Management. Here, we can see that the enrichment policy named Business Policy has been created. However, the policy needs to be executed before we can proceed with creating an ingestion pipeline. We go back to the console, paste the command to execute the enrichment policy, and run it. This command will apply the policy to the reviews data. We get another acknowledged, true response, indicating that the policy has been executed successfully. Next, we create an ingestion pipeline that will enrich the data as it flows from Kafka into Elasticsearch. To do this, we paste the command containing the _ingest pipeline setup, which assigns the business policy to the pipeline. We run the command, and once again, we get an acknowledgement message confirming that the ingestion pipeline has been created. Step 5. Assigning the ingestion pipeline as default. The final step is to assign the ingestion pipeline we just created as the default pipeline for our reviews index. This ensures that any data coming into the reviews index through the Kafka connector will be processed by this pipeline by default. We run the command that assigns the pipeline as the default, and we get the message acknowledged, true, indicating that the operation was successful. Now that Elasticsearch is set up, we can return to Confluent to configure the Elasticsearch sync connector to push data from Kafka to Elasticsearch. With everything in place, the data will be streamed from MongoDB to Kafka, enriched, and finally pushed to Elasticsearch for indexing and analysis. Now let's create the sync connector. First, select the topic reviews db.enriched reviews collection. Click Continue and generate an API key. Be sure to download this key. Next, we need to input the connection details. Go to your Elasticsearch deployment in the Manage Deployment section, navigate to Security, and reset the password for the Elastic user. Copy the newly generated password and paste it into the password field. The user remains Elastic. Now, return to the Manage Deployment section. Find the Yelp deployment and copy the endpoint URL. Paste this URL into the connection URI field. Move forward. And for the Kafka record value format, select JSON. Be sure to change the schema ignore option to true, as we don't want to enforce strict schemas. Before we create the connector, make sure that the index and ingestion pipeline have already been set up in Elasticsearch. If not, the connector will create the index with default configurations, which may not fit our needs. Now click Continue and create the connector. The provisioning process will start, and after a short time, our index will begin receiving documents. As you can see, within a very brief time span, our index has received approximately 3,000 documents. Next, let's go to the Index Overview section and click on Discover Index. We'll create a data view to visualize the data. Name the data view as you like. Choose the index pattern matching your index name and select the appropriate timestamp field. I won't use the time filter in this case. Finally, click Save Data View to Kibana. You'll now see the data presented in the correct format, aligned with the connector and the ingestion pipeline that we previously created. You can search the index fields here using the UI. Now, let's move on to setting up a dashboard in Kibana for real-time visualizations. Navigate to Analytics and select Dashboards from the left pane. We'll create a new dashboard. Start by creating visualizations. For the first visualization, drag the sentiment field to the visualization section. Select Donut as the visualization type. Save it. Next, create a new visualization. Drag the Review ID field and select Legacy Metric as the visualization type. Rename it to Total Reviews and save it. For the third visualization, drag the Stars field. Select Average as the metric and save it. Next, we'll create a map. Drag the business.geolocation field, save it, and add the map to the dashboard. For the fifth visualization, drag the business.city field. Select Tag Cloud as the visualization type and save it. It groups some cities under Other by default, but we'll disable this grouping. Go to Advanced, disable Group Remaining Values as Other, Apply, and save the visualization. Now, drag the business name field, use Tag Cloud again, and disable the other group similarly. Save and return. Next, create a table visualization. Drag Review ID. Set the number of values to 5. And disable Other in the advanced settings. Save it. For the bar horizontal stacked visualization, select stars for the vertical axis and set sum of cool for the horizontal axis. You can add fields for sum of funny and sum of useful as well. Adjust the settings for granularity and save the visualization. Finally, for the last visualization, drag the date field. Use line graph as the visualization type. Adjust the horizontal axis to show weekly intervals and ensure that it's not bound to the global time picker. Save the graph. Set the update interval to a few seconds. Now, let's save the entire dashboard and give your dashboard a name. With the dashboard complete, we can explore our data. You'll see we have nearly 6,400 reviews inserted with an average star rating of 3.8. The tag cloud on the right shows the most reviewed 10 businesses, and the city cloud visualizes the most reviewed cities. Our sentiment analysis shows that 26% of reviews are negative, while 72% are positive. One user has made 6 reviews, making them the most active. Let's drill down to only the positive sentiment records. We see that the total number of reviews is now 4,600, with an average star rating of 4.4. Now, remove the selection. Let's check out Honey's Sit and Eat, one of Philadelphia's most popular businesses. It has 24 reviews, with an average rating of 3.9 stars. We can even see its exact location on the map view. As we explore the data, the dashboard continues to update in real time. Since we started, more than 400 new documents have been inserted into the index, showing that the pipeline is working correctly. Thank you for watching. If you have any questions or need further clarification, feel free to reach out via LinkedIn, Twitter, or email. I appreciate your support, and if you enjoyed this content, please like and subscribe to stay updated on future videos. Your feedback means a lot to me,